to task. All right, let's see here. Let's do some reviewing from the very beginning. Hamiltonian operator, wave function, energy wave function. We're doing lots of waves. There's no potential energy, so that makes this a free wave. The free wave goes on and on forever. It's a particle all by itself in an empty universe that goes on left and right to infinity. Gives it a weird normalization constant, but we don't really need to worry about that. You know, by the way I've been working this is I make sure that all the example problems I give while we're doing free wave stuff, I always make sure the example problems work out that the normalization doesn't matter. Because again, the normalization of a free wave is weird because it's technically 1 over the square root of infinity. Okay, I wanted to actually go over a little bit more about waves. Now, you may recall that a double derivative from math class is technically the curvature of a function. And literally how curvy it is, just by the mere definition of the word. Okay, here's a wave, and it's curvy. Let me point out something. We're going to cover this after the exam, but what I want to point out is that the degree to which this is wavy, this is kind of wavy, tells you it has more energy. Now, to put a better picture of that, I'm going to draw two graphs on top of each other. Right now, this is a graph of a wave function versus x, right? Okay, I'm going to draw on top of that a potential energy surface. So I'm going to draw a new graph, and it has the same x-axis. It has a new y-axis, and that y-axis is potential. Okay, so what I'm going to do with that is I am going to make a potential surface that's going to look like this. There's going to be like a step. There's going to be a step function in potential. Right? And again, here's that new axis. Okay, so now this wave has encountered potential energy. Potential energy is going to rob its kinetic energy, and what that does is it makes the wave slow down, and now it looks like that. It's less wavy. Now, again, we're covering this after the exam. I just want you to go ahead and see it. And in case it's not clear, let me again draw a potential surface graph on top of this wave function graph, and I'm going to actually raise the potential even more. I'm going to raise the potential a little bit more. And what happens is when this wave runs into this potential, it's so big, it just kills it off completely. So anyway, I just want you to see that because this is what we're going to do first thing. And the reason that it's relevant is I hope it makes you understand a little bit more about how the kinetic energy operator works. The wavier something is, since this is a double derivative, it's curvature. This is more curvy than this part, and that's because this has more kinetic energy than this part. The reason that this part has less kinetic energy is because it walked into some higher potential. And I also just want to show you this part. If the potential is really high, it'll kill off the wave function completely. All right, anyway. We also talked about last time, and I know last time, that was one of the roughest lectures. There's one or two that are a little harder, but that was one of the hardest lectures that we had, by the way. This is going to be one of the easiest ones. Okay, so I talked about how the Hamiltonian is special. It gets its own letter H. It gets its own wave function psi. But there's really a bunch of operators, and they have their own eigenfunctions that may or may not be Hamiltonian wave functions. And I talked about that at length the last time. And that was a pretty painful lecture, right? The reason is because wave functions in the Hamiltonian and wave functions of other operators like momentum, they may or may not be the same. And that is the #1 problem with quantum mechanics. And we're going to talk more about it today. In fact, we're going to talk more about it next week. We're not going to ever stop talking about it until we get to the end. Okay, now you know that when you run into this problem, when momentum times sine does not equal a number times sine, the derivative of sine is cosine, right? Momentum is basically a derivative. The momentum operator is h bar over I, a derivative, times a sine function is some jump times a cosine, so that's just blown. When it's blown, you do the average value way, the expectation value way. And again, we talked about that last time. And the reason that works is when when the wave function is not okay with some other operator, it can be expressed as a combination of functions that are okay with that operator. And you can, and because of that, the expectation value way, that's why it will give you a good answer. Anyway, so what else? Okay, so let me give you one example, and then we're going to do a bunch of expectation values just to get used to it, and I'm sure there'll be one on the exam. Sorry, camera problem. All right, so I'm going to give you a stark example of where you definitely need to use expectation values, and this is kind of a brain teaser, by the way. Let's think about position. Where is something, right? Let's ask, where is the free wave, right? The x operator times, let's do a free wave, sine kx. And of course, the position operator says, where are you? Now, you should know that the position operator is x. X hat is x. Same x is right there. That's the same x. Ta-da! So what? Well, this doesn't work, by the way. This is not an eigenvalue equation. This does not look like this. This is operator, function, number. Remember, this has to be a scalar, which is a fancy math word for number, times the same function. All right, now in this case, I see sine and sine, so that's cool. Remember when we did momentum and sine, the wave function didn't boomerang back, and it was shot. So we did expectation value. Here, operator, function, I need to get a scalar. I need to get phi, or pi, or h bar. Actually, almost, when it comes to quantum, everything is either 0, 1, or h bar. But anyway, I need a number, like 0, 1, or h bar, times the function. The function is boomerang back. Not really. You know why? Because that's not a number. X is not a number. X is x. You may be thinking like, oh, well, I guess just make it 5 nanometers, right, units. No, that's arbitrary, right? You can't just decide what the eigenvalue is. Besides, x is just x. Now, before you blow your head off trying to think of like, well, no, hold on, I can figure this out. Actually, no, you can't. The answer is that sine is not the function of the position operator. Now, hopefully you're thinking of like, well, what the heck could be the function of a position operator? How can x times something equal a number times something? It turns out that a branch of mathematics was discovered just to answer that question, because back in the day, they ran into this problem too, and they realized for any of this to work, there has to be a function that when multiplied by x is equal to a number times x. There is. It's called a Dirac delta function. If we have time in an extra Friday hour, I'll show you what it is. But it's a little, it's like a grad school thing, right? It's actually one of the first things I show grad students. And remember, you're, at the end of this class, you're ready for grad school. Maybe some of you will go, maybe some of you won't. And if you're thinking about med school, time to form a new plan, right? Come on, that's kind of stupid. Dental school, pharmacy, those are good choices. If you go PhD route, you're still a doctor, just saying. And you don't pay for grad school if you do PhD, by the way. If you do math, physics, or chemistry, or biology, you get paid to go to grad school. You're still a doctor. Anyway, I forgot what I'm talking about. Oh, the wave function of the position operator is called the Dirac delta function. If you want to look it up, that's fine. I may have time to show you in an extra hour. But given that this eigenvalue equation is not right, it's blown, the results are junk, for a different reason than what we saw before, whatever. The way you solve this is you do the expectation value way. And you always have to do it this way, by the way. You always have to do that with position. So anyway, just expect that. In fact, why don't we do a whole bunch of problems with this, just to get used to doing more expectation values. And today, you know what, I'm just going to blow today on a bunch of practice problems, because I'll have something like this on the exam, and the more we just do this over and over again, seriously, the easier this gets. One of the things about quantum, I've been filming, every time I teach this class, I film it. And I do that mostly just because, because some people can't make it because of something happened. The other reason is that some people tell me they just simply have to watch it twice to get it. And I hopefully, I certainly am trying to explain this the best I can, I just am, but it's still not going to work all the time. That's just the nature of the material. This stuff is just like, sometimes there are great analogies. The fish goes up the stream and that's why Odysseus chased after Penelope. I mean, there's analogies for things that explain everything, and then you get it every time. Sometimes you have to just do things over and over and over again, and then you get them. Guess which one this is, right? This is a class you have to do over and over and over again, and that's why the videos, and today let's just do a whole bunch of expectation value problems. And on top of that, I've brought this up many, many, many times. Let's not worry about free wave. Let's do particle in a box, the thing that I haven't introduced yet, but I keep talking about. Again, particle in a box is something we're going to spend a ton of time on. And I've told you what it is. It's something in a potential trap. Sorry, the potential here goes to infinity, to the left and right of the trap. And we're going to spend a ton of time on this. It's a good model. You can actually describe atoms this way. You can describe things like benzene, like conjugated, I guess dienes is the correct organic word. You can model them with this. You can model an electron like in a diene. So it's like this. So like this is the box. Right, so the electron is here, and it can go there and back and forth, right? So anyway, particle in a box is a really good model for a whole bunch of stuff. So, and I know I haven't formally introduced it, but it's really not too hard to understand, and it's also a really good starting point to maybe do some expectation value questions. So let's do expectation value with particle in a box, and as I've already said a couple of times, the lowest wave is just like the Planck distribution, just like the light bulb. The lowest wave in the light bulb is the same as the lowest wave in the particle in the box. It's just a half sign, right? So remember I was telling you another thing about quantum is you can figure out the wave functions without actually using the Schrodinger equation. Half the time that's how you do it, which is crazy, but that's how it works. So in this case, I can just look at this trap. I can see it's a light bulb, and I know that the lowest wave, the longest wavelength, the lowest energy, the first state, the ground state, is just half sign, right? So I know that. Okay, with that, remember I can even just look at it. Just look at this and figure this out. A half sign goes from 0 to pi. Of course, it's a function of x. So when x goes from 0 to L, sine needs to go from 0 to pi. See, I just figured out the wave function. This is correct, by the way. Okay, so let's do the expectation value of x. Now, the complex conjugate, I swear to God, maybe I'll put this on the exam. Sometimes I put, what's the complex conjugate of x? And people really get upset. It's x. The complex conjugate of whatever is wherever you see the letter I, write minus I. Even if it's minus I, then you write minus I plus I. What happens when there's no I? Like in this case. Sine x, complex conjugate. I'll just write up the whole thing. All right, what's the complex conjugate of sine? It's just sine. It's just sine. Sine, let me just write sine squared. Oh, that it's terrible. Okay, particle in a box. Now, normally I would have written minus infinity to infinity, but no, the limits are 0 to L. Okay, so there you go. Right. So anyway, look out for that complex conjugate thing, right? If this was sine ix, then the complex conjugate would be sine minus ix, but by itself, I don't see the letter I, so you just don't do anything. So this is sine x sine, which is sine squared x. All right, then that's not hard to, in case, again, if your math is really rusty, x sine squared integrated is the same as sine squared x integrated. The order doesn't matter. If you're not sure about that, use those websites. In fact, use that website, use that Wolfram website, and integrate this sucker, right? When I have you do questions, homework questions, you'll use you'll use the Wolfram website to do this. I think that you actually did cover how to do this stuff, like substitution, trigonometric substitution to do these intervals. No, just use a website. On the exam, there's identities. So anyway, and so we do that, and what do we get? We get L squared over 4. There we go. So that's the average value. That's the average position. But you know what? Hold on. I see a couple of things wrong. Just like I am confident enough to look at this damn thing and figure out that the wave function is sine pi x over L, I can see that on average it's in the middle. Like, if I take the average value of this function, I bet it's right in the middle. I mean, just look at it. And this is L over 4. No, wait, it's L squared over 4. Now hold on. Think about Maxwell-Boltzmann. When we did the average velocity, that damn thing had units of velocity. I think that was on the homework question. Anyway, when it was velocity squared, that little square root thing went away. The units of average velocity squared had units of meters squared per second squared. This is average position. It should have units of nanometers. But this is nanometers squared. Uh-oh, it's like I intentionally worked the problem wrong. Why? Because on your exam, the first section are problems, solutions that are wrong, and you identify what's wrong. So what's wrong? I spent a good part of, 2 lectures ago, talking about normalization. How you can figure out wave functions. You just saw the trap. You saw the trap. You can often figure out the wave functions, but that doesn't come with a normalization constant. You can't forget to put it in yourself. Now, I happen to know how to normalize it, and it will be, if you need to know the formula, it's on the exam. If not, whatever. So the correct normalization is the square root of the integral of the function squared. Complex conjugate function, but in this case it's just sine squared. Okay, so this is the real wave function. All right, now what we do is the business end stays put. Nothing happens. All right, what's this on bottom? Use a website, use an identity, look it up, and what you get is square root of L over 2. And just like Maxwell-Boltzmann, this is a little awkward, so don't forget to flip it. And what you see is that it has units of, it's basically square root of the units that it describes, right? Kind of like Maxwell-Boltzmann, we talked about that. Okay, so that's the right wave function. Okay, so had we normalized it to begin with, here, I'll just keep working down. Had I not done what I did, which was to forget the normalization constant, what I would have actually integrated is this. Had I not forgotten the normalization constant, I would have had 2 over square root of L times, the function appears twice, right? Sine squared, so you get 2 normalization constants. Okay, so this is the same, just like I described last time. Of course, it still integrates to the same thing, so this is 2 over L. It still integrates to L squared over 4, and this ends up being L over 2, which makes sense because I'm just drawing this again. Oh, sorry. What's wrong with me? There's the wave function, and on average, it's in the middle. Right. Of course, the middle is L over 2. Okay, makes perfect sense. So, you can see the importance of normalization. You really need to know the normalization constants when you're doing expectation values, by the way. Now, you may have noticed that you do not need to keep track of normalization when you're using the eigenvalue way, because the wave function's on the left and right, and that includes this normalization. That's a homework question, I just gave you the answer. Anyway, it's a homework question coming up after the exam, but I just gave you the answer just for the hell of it. Okay, anyway, so practice, right? Practice, and then you're just going to do more questions just like this. There is a bit of a formula to it, so just do this. Why not just do this on your own, right? And it doesn't matter because there are tons of homeworks that are just like this. Do it over and over and over again, and when it's on the exam, it won't be the same, but it's just, there's a method to it, right? It's not that bad. Okay, now I could do more examples, but then it really does get superfluous. So, like Maxwell-Boltzmann, let's think about what else you can do with probability distributions times the things you want the average of. Like I just talked about average velocity squared. Can I get the expectation value of position squared? Sure, let's do that. Okay, so like last time here, I'll write it out. We'll do particle in the box. And you know what, just, I know I was rushing. So let me write it out all formal and nice, which is, maybe I should have done that already. Actually, I'm writing this down because, again, I want to make sure that you don't forget this complex conjugate deal. Okay, the x operator times the x operator, which is the x operator squared, is just x squared. And again, that's like, wait, is that more complicated? That sounded like stupid simple. It's stupid simple. Don't let that little hat, don't let a little hat for an operator make it more complicated than it is. Okay, there we go. Okay. So expectation value of x squared. All right. Square root of 2 over L, square root of 2 over L, 2 over L. Here are the L, sine squared. I can put x squared in front, or I can put it behind. All right. As like last time, what am I going to do? I am going to simply use a website to figure this out, and it ends up being a little complicated. It's kind of annoying that it's so complicated, but whatever. I mean, it does what it wants to do. All right, let me. Okay, so all right, so it's a little complicated. That's fine. It has the proper units of length squared. All right, so what? Here's the so what. So yes, I can calculate it, and sometimes I do that for the hell of it. But you might recall that in statistics, and I've said to you a couple of times, I haven't said it in a while, but I said it at the very beginning a couple of times, that quantum is a theory of probability. In fact, I told you the whole course is about probability, using probability in physical science. Okay, now you may recall something called a variance, which is a sigma squared. Now, you may recall sigma is the error bar on your graphs, right? And so the square of that's a variance. Now, the reason variance is a thing is because that's what you calculate. Right, you have n data points, and so here's the formula for variance, and you may recall this. Okay, so square, right? So your data set minus the average, take all of the differences and square them, and divide by the number of data points, and that's your variance, and that's sigma squared. Your error bar for when you're taking data. Guess what? Maybe you've seen this, maybe you haven't, but it's equal to this. This is usually the easier way to calculate it, by the way. The average of the square minus the square of the average. Remember Maxwell-Boltzmann again? We did b squared, average of the square of b, and we compared that to the average of b, so you have to square one or take the square root of the other anyway. They weren't the same. And I was saving this, you weren't ready for this at the time, but the reason that when we were doing Maxwell-Boltzmann, that the RMS velocity is not the same as the average velocity is because there's a variation in the speed of the gas molecules, right? So here's the spectrometer again. I got to remember to do that. Anyway, here's the spectrometer again. Some of those gases are not moving quickly, and some of them are, right? Because of that, the average velocity squared, the RMS velocity is not the same as the average velocity. It's the variance in speed. All right, so notice that when it comes to this particle in the box, I can calculate this. I've already done this part. Therefore, the variance in x is, which I've just done. And what's this? It is, damn it, now I gotta write that down again. I shouldn't, if I planned this better, I wouldn't have to do this. Okay, L squared. Okay, the average x was L over 2, so that's L squared over 4. And this ends up, I'm not gonna factor this in my head, I'm gonna completely get this wrong. That ends up being pi squared minus 6 over 12 pi squared L squared. Okay. All right. So there you go. I can calculate the variance in this particle in this particle in a box wave function. It's actually surprisingly convenient that I have the drawing right there. So what? Now I hope that when I was talking about velocity, the average of the square minus the average squared, when it comes to velocity in our gas example, our Maxwell-Boltzmann, it makes sense that there's a variation in the speed of the molecules, so you can just kind of visualize that, right? If I have a balloon, some of the gases are moving quickly and some of them are not. Some of them are moving very slowly. Therefore, there's a variance. Very simple. Okay, now when it comes to a particle in a box, let me show you what that means. That would mean that, let me draw two wave functions. I'll draw like the one I just had, and let me draw one that's more narrow. Okay, the difference between these two is that this has a wide variance. In fact, that would be what I calculated here, and this has a narrow variance. So if I calculated it for that, I would get a smaller number. Now what that means is that in terms of certainty of position, if I was to do a measurement on some kind of spectroscopy, single photon, single atom imaging, which we can do that kind of stuff now. Single photon this, single atom that. We do that kind of stuff all the time now in the past 10 years. And I could perhaps try to figure out where this particle is, or where the electron is in the conjugated diene, right? So anyway, I can figure out where the particle is, and I can tell you that I can do the experiments a bunch of times and I'd never get the same answer twice. That's what a wide variance would mean. Now, if I was doing this guy here, whatever reason that the wave function looks the way it does, when I make the measurement, I actually wouldn't get such variation. I would almost always get that the particle is like dead center. All my measurements would be right about the dead center compared to this guy where I can likely see the particle just about anywhere except right towards the end. So you see that the implications here is that a wider variance means that I'm not, if I do some kind of measurement, I'm going to never quite get the same thing twice. The particle is always kind of anywhere between 0 and L, whereas if I have a wave function like this with a low variance and narrow variance, every time I do an experiment, it's always like the spectrometer says, oh, the particle's kind of like right near the center. It's always near the center. So that would be the implication of how these wave functions relate to my experiments. And in this variance that we know how to calculate using quantum mechanics tells us what we would get. So now I don't need to do the experiment, which, by the way, this is kind of a little factoid. It turns out that this is what theoreticians are trying to do, like the justification for people who do nothing but theory is that once they get really good at it, and have supercomputers that you won't need to do any experiments anymore. Now, the problem they ran into, by the way, is that to calculate properties of like decent-sized molecules, like benzene or toluene, they need a supercomputer. To do a good job with a protein, you need a computer that exists 1,000 years in the future. So once they figured that out, they were kind of screwed. But anyway, little factoid there. All right, now let's go a little further. Position is just one operator out of many, right? We also have momentum operators. So it turns out that I'm perfectly capable of calculating the spread of momentum, the variance in momentum of a particle in a box wave function too. And I know that actually the momentum, we've done this one before, right? So the particle in the box is a sine wave, and I know that the average momentum of a sine wave is 0. And remember, we brought this up, this was brought up before. The particle in a box momentum has to be 0 because it can't leave the trap. Remember when I talked about that a while ago? So anyway, sorry, camera problem. All right, so we are going to do the variance and momentum. All right, so because we can. What are we going to get? Well, the formula for variance is this, and I, of course, will have that on the cheat sheet. There you go. But tell you what, let me switch examples. Because we all know that momentum from last Friday, momentum and sine, that's such a pain, right? So tell you what, let's just pick a different problem. Let's do a free wave. Let's do a free wave problem. Let's do the variance momentum of a free wave. This is way easier. And you know why? It's so much better to do free waves and momentum because we can do it the eigenvalue way. And remember, we have to do expectation value way with sine functions, like the particle in the box is a sine function. Okay, and this, of course, is h bar k. See, I told you I really like doing things by expectation values when I can. Eigenvalue equations. I hate expectation values. Okay, one reason to do this is to remind you of, this is going to come up. So now I have to do momentum squared. And what that is momentum. In case it's like, if you think there's some secret to this, it's just momentum. So that's h bar over I ddx, h bar over I ddx, e to the I kx. And you're going to see expressions more and more like this as after we get past the exam, obviously. Okay, the constants can all come out, so that's minus h bar squared. H bar squared over I squared is minus 1, so that's h bar squared over minus 1. Okay, derivative x is the double derivative. All right, again, it's just, think of what is the easiest possible thing it could be, and that's what it is. Okay, so then what I get is double derivative of e to the ikx is ik e to the ikx. I squared, k squared. And this, of course, is minus h bar squared times minus 1 times k squared is h bar squared, k squared. Okay. The point of this is the variance in momentum for this free wave is, I don't need that anymore. It's h bar squared, k squared minus the momentum is h bar k squared. Okay. So there's no variance in momentum. But now let's make an interpretation. There's no variance in momentum. That means that there's no lack of knowledge of momentum. This thing is moving at a certain speed always. That came out better, didn't it? There's no variation in momentum, and therefore this particle is moving with a certain speed now and forever, and always will and always had. So, cool. No uncertainty in momentum. So if maybe a whole bunch of particles has this wave function, all of them have the exact same speed. So all of these are saying the same thing. All right, now, tell you what if we were to calculate this for e to the ikx? Okay, it's a little bit harder, and I'm going to have to do this with the expectation value way. But I can already go ahead and tell you, heads up, it'd be infinity. It'd be infinity. And I'm not even going to bother to try to calculate it, because here's why. The wave function squared, absolute value of the wave function squared, which is the probability, is the wave function complex conjugate times the wave function, which is e to the minus ikx, e to the ikx. And if you're not sure what that is, I have on the exam identities like this. And so therefore this is e to the minus ikx plus ikx is e to the 0. And of course, identity on the exam tells me that e to the 0 is 1. And therefore, when I look at the wave function, absolute value of this wave function, and here's the x coordinate, it's 1 forever and ever and ever. Okay, forever to the left, forever, I can't draw this obviously, forever to the left, forever to the right, it's just some value. And if you integrate that times x, what you get is infinity. So again, without going through all the bloody mathematics, because unfortunately this one gets a little complicated, heads up. The uncertainty in position is infinite. I have no uncertainty in momentum. I have infinite uncertainty in position. Now the uncertainty in position, instead of doing it mathematically, I want to point out that the wave function, the probability density, never changes infinity to the left, and it never changes infinity to the right. So how could you ever know where it is? It's equally probable that it's anywhere and everywhere all at the same time. Therefore, I conclude you have no knowledge of where it is. And again, if we did all the bloody math, and actually you're going to do it like on problem set 8, by the way, when you get much better at mathematical this and that, I will have to do this, but it comes up later, you're going to find that the variance is infinity. Okay, what is the point of all this? The point of all this is that there's actually a relationship between the variance and momentum and the variance in position. So we're just getting a lot of practice doing these. We're doing them different ways, but there's a reason for it. And the reason is that let me express this 2 different ways. And then we're going to do a bunch when the exam is over. This is what we're going to launch into immediately after the exam. And it does, remember I told you that we start quantum mathematically is not too bad, but it gets turned up. Well, after the exam it gets turned up a little bit, and this is how. What you're seeing is a manifestation in the Heisenberg. I'm not talking about math. I'm not talking about math now. Heisenberg uncertainty principle. Okay. Actually, the bad guy in the Little Elf show is that's Gus Fring. I don't know if you noticed that. My family actually knows him. He lives in upstate New York. That's where my family's from. Anyway, so I know Gus Fring. So what about this? Okay. What it means is that, let's go back to our particle in a box. What happens is, let's look at the one with the wide certainty and variance, and a little uncertainty, a little variance in position. Okay, what about these? This is large variance in x, and this has a low variance in x. It turns out the Heisenberg uncertainty principle states that since this has a large variance in x, and you're not sure where it is, it's going to have a low variance in momentum. And on the homework, when you come back, you're actually going to calculate that. You're going to calculate the variance in x and the variance in momentum. This thing has a low variance in x, and guess what? It has a high variance in momentum. So if one is big, the other is small. If the other is small, the other is big. Oh, like large, I don't want to do the high, low, high, low. Anyway, they're anti-correlated. So what that means is, the mathematical expression of this is the variance, the variance in, sorry, I'm not writing this out well. The variance in x times the variance in momentum is a constant, right? And that's why if one of these is large, the other has to be small. And they have to balance each other out to be approximately constant. That's what the Heisenberg uncertainty principle says. Now, when it comes to here, if you don't know where it is, you actually know how fast it's going, right? For all the reasons I just said, that think of the extreme, a low variance in momentum, like the free wave, you know exactly how fast it's going. So low variance means you know how fast it's going, but that means you don't know the position. Here, you know the position, but again, as you do your homework, you're going to find that it has a high variance in momentum, meaning you don't know how fast it's going. So you can't know where something is and how fast it's going, which is, hopefully you've heard that before, that's the Heisenberg uncertainty principle. Now, you've also learned enough mathematics to calculate this, right, because you know how to do expectation values. Okay, what I'm going to end on, because I think I've probably gone over here quite a bit, is that this is really kind of neat how this works. So again, we can calculate variances, and we've done a bunch of variances. We've done them for position and momentum. I know I've kind of been a little scattershot in my examples. I just want to make sure you can calculate them. So there's this aspect, but now here's another aspect. The uncertainty principle does a bunch of stuff. Here's what this means. If you were to do an expectation value of like position momentum, and then you were to calculate the expectation value of, they get little hats, they need hats, and then you would do the expectation value of momentum and position, you know what? They're not the same. Oh, that looks awful. They are not the same. Okay. So, without worrying about how you calculate this looks like a bit of a pain. But I know enough quantum mechanics now to read that this is an expectation value, and what is being queried is position and momentum. Momentum and position, and here queries position and momentum, right? Now, this is like saying I'm going to do two experiments. You're going to measure the velocity of something, and then I'm going to see where it's at. And here I'm going to see where something's at, and I'm going to measure how fast it's going. I would normally say that it wouldn't matter which one I do first or second. In fact, in my knowledge of physics and whatnot from high school and college, I would say that it can't possibly matter which one you do first and which one you do second. The Heisenberg uncertainty principle says these are not the same. So it does matter which one you do first or which one you do second. Now, the implications of that are, because it shouldn't matter, but it does, that means you can never really know. If you can't do this and get the same as that, and it's not meaningful which one is done first, right? It doesn't matter to me whether I measure position or momentum first. There's no intrinsic reason why it's right to make one measurement first and then another measurement second. There's no reason to pick one or the other. Doing it one way isn't right compared to another. But they don't give the same result. And that's like a major problem. What it means is that you can't know both simultaneously with absolute certainty. There's another way to describe it. And I'm not going to bring this up again. This is kind of, I have to show you grad school stuff. But it turns out that these measurements change the system. Right? Now again, I'm not going to say too much about this. I'm not going to bring it up again. This is a grad school level thing, but it may be further. When you make measurements on quantum mechanical systems, you change them. That's why this doesn't work. When you measure how fast something is going, when it's quantum mechanical, you'll change its position. That's why the subsequent measurement of position is not the same as when you measure it first. By the way, when you measure where it is, you change its speed. So now you screwed that guy. So you can never win, right? Now here's the next thing. You may be thinking like, okay, so what's the clever solution to that? There isn't one. This is and is. There is no solution to this. You have to accept the fact that you can never know where something is and how fast it's going at the same time. You can only do some kind of weird balance between the two. And it's up to you how to balance that depending on what it is you're trying to measure. Now you may be thinking like, well, who cares about this kind of stuff? Companies like Intel, AMD, chip makers. You know why? Because quantum mechanical objects include electrons. The speed of an electron, that's the voltage. It's related to the voltage. Position, where is it in the chip? Those folks, the places you want to work, because those are really good jobs, high-paying jobs, this is the stuff that they worry about. This is what they model. That's why they have these supercomputers. They're using chips to figure out how to make other chips, and they have to solve this problem because that's how the freaking chips work. So anyway, so that's a little motivation for you there. I think I have a little bit more time, so I wanted to tell you a little bit more about whoops, I have gone way over time. I actually kept talking another 20 minutes. So when I realized that, I had to come back and film this. All right, I'm cutting off the test from here, obviously. Wednesday is your exam review, and I swear to you, I'm going to be giving all kinds of hints. I will have written the exam by then, and I can't help it. I'm going to be spilling out all kinds of hints and cheat codes on how to pass that exam. So, there's nothing else to say, so I will see you all then.